Air defense does not work in the dark. It works on radar returns, the electronic picture that radar stations build of the airspace above the battlefield, the tracks that allow air defense operators to identify threats, assign engagement priorities, and direct their missiles toward targets they cannot see with their own eyes. Take away the radar picture, and air defense operators are left with acoustic detection, visual observation, and the kind of fragmented situational awareness that makes effective engagement of fast-moving drone threats nearly impossible. In early May, Ukrainian forces took away exactly that picture from a section of the Eastern Front. A Russian Podlet-K1 low-altitude detection radar, the system that had been tracking Ukrainian drones and providing targeting data to Russian air defense complexes across a significant sector, was found, tracked, and destroyed by Ukrainian kamikaze drone operators who had spent days listening to its emissions before they destroyed the antenna that produced them. What followed in the sector's airspace was immediately visible to Ukrainian drone operators who had been managing restricted flight profiles to avoid Russian air defense coverage. The constraints lifted. The altitudes that had been avoided became accessible. The approach angles that had been forced by Russian air defense coverage of the sector reverted to the profiles that Ukrainian operators preferred for effectiveness rather than survival. The radar gap that the Podlet-K1's destruction created was a gap that Ukrainian forces filled immediately, with reconnaissance missions that had been degraded, with strike missions that had been rerouted, with the operational freedom that the radar had been systematically denying. This is the story of how Ukrainian operators found that radar and what its destruction cost Russia. The Podlet-K1 is a mobile low-altitude surveillance radar designed specifically for the threat environment of modern warfare. The low-flying drones, cruise missiles, and helicopters that operate below the detection threshold of higher-altitude search radars. Its design reflects a specific operational problem. Conventional air defense radars, optimized for detecting aircraft at altitude, have poor coverage of the low-altitude band, where terrain masking and ground clutter reduce their effectiveness. The Podlet-K1 fills that gap with specialized signal processing that distinguishes low-altitude moving targets from the background clutter of the ground environment. In the context of eastern Ukraine, where Ukrainian drone operations are primarily conducted at low altitudes to exploit terrain masking and reduce exposure to Russian air defense, the Podlet-K1 is directly targeted at exactly the threat category that Ukrainian forces rely on. It is the system that gives Russian air defense the ability to track Ukrainian FPV drones, reconnaissance drones, and the low-altitude strike platforms that have become central to Ukrainian military effectiveness. Without it, Russian air defense coverage of the low-altitude band in its sector degrades substantially, creating the gap that Ukrainian forces exploit. Ukrainian electronic intelligence teams had been monitoring the sector for the Podlet-K1's emissions for several days before the strike. The system's radar transmissions, necessary for its function and distinctive in their frequency and pulse characteristics, are detectable by electronic intelligence assets that know what to look for. Russian operators using the Podlet-K1 apply emission control procedures to limit their detection exposure, operating intermittently, using reduced power modes when full power is not required, varying their transmission patterns to reduce the predictability that sustained emission would create. These procedures reduce the detection risk. They do not eliminate it. Ukrainian electronic intelligence collection built the targeting picture from the accumulated emissions, each transmission adding a bearing line, each bearing line from a different collection position adding another constraint, the intersection of multiple bearing lines from multiple collection events, narrowing the estimated location to a zone small enough for visual drone observation to confirm. The process took several days because the Podlet-K1's emission control procedures reduced the frequency and duration of emissions that collection could exploit. It produced a precise location because Ukrainian collection assets were patient and thorough. The visual confirmation came from a reconnaissance drone that searched the estimated location zone and found the specific vehicle configuration of the Podlet-K1, the large rotating antenna assembly on a dedicated vehicle platform, the associated processing and power vehicles positioned nearby, the specific profile that Ukrainian analysts had trained against from previous observations and from open-source technical documentation of the system. The confirmation was made from altitude, with the drone managed to minimize its own radar cross-section exposure to the system it was targeting. Ukrainian commanders who reviewed the targeting picture authorized the strike. The specific challenge of engaging a radar system is that the most valuable component, the antenna and its associated signal processing hardware, is the most exposed element of the system. Mounted externally on the vehicle where its rotation can provide 360-degree coverage. This external exposure, which is an operational requirement of the system's function, is also its primary vulnerability. A precision strike that destroys the antenna assembly eliminates the system's operational function even if the vehicle platform survives. The strike package used 2 kamikaze drones in sequence. The first targeting the antenna assembly to eliminate the system's primary function, the second targeting the processing vehicle where the signal processing electronics are housed. Destroying both components ensures that the system cannot be partially restored by replacing one without the other. The antenna is the sensor. The processor is the brain. Both gone means the system cannot be reconstituted without full replacement. The first drone approached the antenna assembly from below the antenna's rotation plane, the approach angle that minimized the probability of triggering the radar's own self-protection systems before the drone reached lethal range. The approach used terrain masking on the final segment, emerging from behind a tree line at close range to reduce the reaction window available to the crew. The strike hit the base of the antenna mount, collapsing the assembly. The antenna fell. The processing vehicle was struck by the second drone 12 seconds later. The strike hit the electronics bay. The processing vehicle's systems, the signal processing hardware, the display systems, the data links to associated air defense complexes, shut down as the vehicle's electrical and structural integrity failed. The Podlet-K1 ceased to function. The air defense complexes in the sector that had been receiving data from the Podlet-K1 lost their low-altitude track picture simultaneously. The operators at those complexes, the Buk, Tor, and Pantsir crews, who had been maintaining engagement readiness against the targets that the radar was tracking, found their displays showing only the incomplete picture that their own shorter-range sensors could provide. The low-altitude coverage zone that the Podlet-K1 had been maintaining across a wide sector of the front went dark. Ukrainian drone operators in the sector noticed within hours. The flight profiles that had been restricted by Russian air defense coverage, the altitudes and approach angles that Ukrainian operators had been avoiding because the Podlet-K1's coverage made them high risk, became available again. Reconnaissance missions that had been conducted at degraded altitudes to stay below the radar's coverage ceiling were reflown at optimal altitudes, producing observation quality that the restricted profiles had been preventing. Strike missions that had been routed around the radar's coverage zone used more direct approach angles that reduced flight time and improved strike accuracy. The operational cascade from the radar's destruction extended across every Ukrainian drone mission in the sector for the days until Russian forces could either repair the destroyed system or deploy a replacement. Those days represented a window of reduced Russian air defense effectiveness that Ukrainian forces used to conduct operations they had been unable to conduct under the radar's coverage. Now let us examine what Russia lost. The Podlet-K1 radar system carries an estimated replacement cost of $25 to $40 million USD per unit, reflecting the sophisticated signal processing electronics, the specialized antenna assembly, and the integrated software systems that allow it to distinguish low-altitude drone targets from ground clutter. This cost range places it among the most expensive individual systems lost in single engagement events, more expensive than most individual armored vehicles. Comparable in cost to the air defense systems it was supporting. The specific electronic components that make the Podlet-K1 effective, the signal processing chips, the high-frequency electronics, the software-defined radar processing systems, are precisely the categories of technology most restricted by Western export controls. Russian domestic production of equivalent components is constrained, and the alternative procurement channels available under current sanctions conditions provide limited quantities at elevated cost. A destroyed Podlet-K1 represents not just a procurement cost, but a production challenge. The replacement may take months to manufacture and deliver under current Russian defense industrial conditions. The crew specialized in operating the Podlet-K1. The radar operators, the maintenance technicians, the signals intelligence personnel who manage the system's electronic parameters represent a training investment that is not quickly regenerated. Radar operation at this level of technical complexity requires specific training pipelines that take 12 to 18 months to produce qualified operators. The experienced crew lost with the system adds to the replacement timeline, since a new system staffed with untrained operators performs at reduced effectiveness until operators develop proficiency. The operational value of the low-altitude radar coverage that the Podlet-K1 was providing cannot be captured in its replacement cost. The system's function, detecting the Ukrainian drone threats that are most operationally consequential for Russian ground forces, has a multiplier effect on the entire Russian air defense posture in the sector. Air defense complexes without low-altitude radar coverage are significantly less effective against the specific threat categories that Ukrainian forces are deploying. The degradation of those complexes' effectiveness during the period of the radar gap represents an operational cost that compounds the direct material loss. Ukrainian electronic intelligence specialists spent days building a targeting picture from intermittent radar emissions. Ukrainian kamikaze drone operators flew a Sequence 2 drone engagement that destroyed both primary components of the system within 12 seconds. Ukrainian drone operators throughout the sector used the resulting gap to conduct operations that had been restricted by the system's coverage. The Podlet-K1 that had been watching Ukrainian drones is gone. The airspace it was watching belongs to Ukrainian operators again. Russia built a radar to see Ukraine's drones. Ukraine found the radar by listening to it. Ukraine destroyed it. And the drones that it had been tracking are now flying the profiles the radar had been denying them. Ukraine listens. Ukraine finds. Ukraine frees its drones from the coverage that was constraining them. The radar is gone, the sector's airspace is open, and Ukrainian operators are using every meter of it. To understand the full significance of this engagement, it is necessary to examine the specific architecture of Russian air defense in eastern Ukraine, and why the low-altitude radar is the component whose loss is most consequential for the system's overall effectiveness. Russian air defense, in the operational area, operates as a layered system. Multiple weapon platforms with different range and altitude capabilities integrated through shared radar data that allows operators at each platform to see the full threat picture rather than only what their own organic sensors can detect. The Book M2 provides medium range, medium altitude coverage. The Tor provides short range, low to medium altitude coverage. The Pantsir provides very short range, very low altitude coverage with its gun missile combination. Each system has strengths and limitations in its coverage envelope, and the integration of their data through shared radar networks is what allows the overall system to present a coherent defensive picture against the diverse drone threat categories Ukrainian forces employ. The Podlet-K1 is not a weapon in this architecture. It is a sensor, the dedicated low-altitude surveillance radar that feeds target tracks into the shared data network, allowing every air defense platform in the sector to see low-altitude threats that their own organic radars would miss or detect at reduced range. When the Podlet-K1 is operating, a buck crew whose own radar has poor low-altitude performance receives tracks of low-flying drones from the Podlet and can engage them at ranges beyond what their own radar would support. When the Podlet-K1 is gone, those buck crews are limited to their own radar's degraded low-altitude performance. This cascading effect, the degradation of every air defense platform in the sector when the dedicated surveillance radar is destroyed, is the specific operational leverage that makes the Podlet-K1 such a high-priority target. Destroying the Podlet does not eliminate any of the weapon platforms. They are still present, still armed, still capable of engaging targets their own sensors detect. But their effective engagement envelope against low-altitude threats is reduced, and the sector of sky they can collectively defend is reduced with it. Ukrainian drone operators who noticed the change after the Podlet's destruction were not experiencing the complete absence of air defense threat. They were experiencing a reduced threat, one where the coverage gaps in Russian air defense had expanded from the specific limited gaps that skilled Ukrainian operators had been exploiting to larger gaps that allowed broader operational freedom. The difference between operating in a sector with a fully functional Podlet-K1 and operating in one without it is the difference between flying in a sector where every move is tracked and every altitude is covered, and flying in one where the tracking is degraded and the coverage has holes that experienced operators can find and use. The specific engagement of the Podlet-K1 with kamikaze drones rather than other available strike methods reflects a deliberate choice that Ukrainian planners make based on the specific characteristics of high-value electronic targets. Artillery fires against a radar station risk destroying the antenna assembly, but may not achieve the precise structural damage required to eliminate the processing equipment and data links that constitute the system's operational value. The blast and fragmentation effects of artillery are effective against personnel and vehicle platforms, but less reliably effective against the electronic systems inside hardened or protected vehicles. Kamikaze drones that can be directed to specific aim points on specific vehicle components achieve the precision that maximizes the probability of complete system destruction rather than damage that Russian crews might repair. The sequencing, antenna first, then processing vehicle, reflects the specific priority assessment that Ukrainian targeting planners applied. The antenna is the primary operational component. Destroying it immediately eliminates the system's radar function, but an antenna can potentially be replaced from field spares if the processing vehicle survives. Destroying the processing vehicle 12 seconds later ensures that even if Russian crews could somehow replace the antenna, they have no working system to connect it to. Both components must be replaced together, and the replacement process requires the full factory support that field maintenance cannot provide. Russian air defense specialists who operated the Podlet-K1 had managed the system's emission patterns carefully throughout its operational deployment. The intermittent emissions that Ukrainian collection required several days to localize represent the specific trade-off that radar operators make between operational effectiveness and emission security. The more the system transmits, the better the picture it produces, but the more it transmits, the more exposed it is to direction finding by exactly the kind of electronic intelligence operation that found it. The operators who kept the system alive through several days of Ukrainian collection were doing their jobs correctly. What they encountered was a Ukrainian collection operation that was patient enough, thorough enough, and technically capable enough to build the targeting picture from the reduced emission schedule they were using. The days of collection that Ukrainian electronic intelligence invested were the price of finding a target that was actively trying not to be found. The investment was justified by the operational gain of the sector's restored airspace. The replacement process for the destroyed system will be constrained by the same factors that limit Russian replacement of every advanced electronic system destroyed in Ukraine. The Podlet-K1's specialized components, its phased array radar elements, its signal processing hardware, its software systems are manufactured to military specifications that civilian supply chains cannot easily substitute. Western export controls have restricted the flow of the specific microelectronics that Russian military radar production requires. The effective replacement timeline for a destroyed Podlet-K1 under current Russian industrial conditions is measured in months, not weeks. During that replacement period, the sector's low-altitude air defense coverage remains degraded. Ukrainian drone operators continue to use the expanded operational freedom that the radar gap provides. Reconnaissance missions gather better data. Strike missions take more direct approaches. The cumulative operational benefit of the extended gap compounds over the weeks between the system's destruction and whenever a replacement can be deployed. Ukrainian electronic intelligence listened to the Podlet-K1's emissions for days. Ukrainian analysts triangulated its location from the signals. Ukrainian drone operators found it visually. Ukrainian kamikaze drones struck it in 2 precise sequential hits. Ukrainian drone operators in the sector flew free in the gap that followed. Russia built a radar to track Ukrainian drones. Ukrainian forces found the radar, destroyed it, and flew their drones through the airspace it had been defending. Ukraine hears what Russia uses to see it. Ukraine destroys what hears and sees. Ukraine holds the sky above the ground it is defending. The Eastern Front in early May has one less Russian radar tracking Ukrainian drones. The drones are flying. The front holds beneath them. There is a final dimension of this engagement that connects the electronic intelligence work and the kamikaze drone strikes to the Ukrainian soldiers and drone operators whose operational environment improved when the radar fell. Every Ukrainian drone operator who had been flying restricted profiles in the sector, lower than optimal, rerouted around coverage zones, accepting degraded observation angles to stay below the radar's detection threshold, was managing a daily operational tax. Each mission cost more planning time, covered less ground effectively, and produced lower quality results than the same mission would produce without the radar's constraints. Across dozens of missions over the days and weeks the radar had been operating, that tax accumulated into a substantial reduction in Ukrainian drone operational effectiveness. The Ukrainian electronic intelligence specialists who tracked the radar's emissions were not simply finding a target. They were working to eliminate that daily operational tax for every drone operator in the sector. The targeting work they did over several days returned to Ukrainian operators the flight profiles they needed, the altitudes that produced better observation, the approach angles that made strike missions more effective. The drone operators who flew the restored profiles in the days after the radar's destruction may never know specifically what changed or why. They know their operations are less constrained. They know the approaches that were previously high risk are now accessible. They are using the restored freedom to do their jobs better than they could before. That restored effectiveness, multiplied across every mission in the sector during the period the radar gap persists, is the downstream product of Ukrainian electronic intelligence patience and 2 kamikaze drone strikes. Ukraine finds the system that constrains its operators. Ukraine destroys it. Ukraine restores the freedom that it took. The radar is gone. The operators fly free. The front holds with the full reach of Ukrainian drone capability restored above it. One more dimension of this engagement deserves examination, the dimension that concerns the future, and what the destruction of this specific radar means for how Russian air defense planners approach the Eastern Front going forward. Russian air defense commanders will respond to the loss of the Podlet-K1 with a combination of tactical and technical adaptations. They will increase the emission security measures on remaining radar systems, tighter emission control protocols, shorter transmission windows, more aggressive frequency management to reduce the collection window that Ukrainian electronic intelligence can exploit. They will attempt to relocate surviving radar assets more frequently to reduce the sustained observation that targeting requires. They will explore alternative methods of low-altitude surveillance, passive detection systems, acoustic sensors, and networked ground observation that might partially replace the electronic surveillance capability that the Podlet provides. Each of these adaptations has costs. Tighter emission control protocols reduce the radar's operational effectiveness. A system that transmits less frequently produces a less complete air picture for the air defense complexes it supports. More frequent relocation increases vehicle wear, fuel consumption, and the logistics overhead of maintaining a system that is constantly moving. Alternative surveillance methods provide partial but not equivalent capability replacement, and Ukrainian electronic intelligence will be watching and adapting to each of these responses, developing new collection approaches to work around tighter emission control, extending the patience of surveillance operations to accommodate more frequent relocations, and identifying the specific vulnerabilities of whatever alternative surveillance methods Russia deploys to fill the gap. This is the ongoing competition that shapes the electronic dimension of the conflict. Neither side finds a permanent solution. Each adaptation generates a counter-adaptation. But the competition is running against Russian air defense in the sense that each Russian system destroyed must be replaced from production lines under strain, operated by crews that take months to train, and protected against a Ukrainian collection and strike capability that continues to improve with each engagement. The Podlet-K1 that was tracking Ukrainian drones in early May is one point in that competition. Its destruction represents a Ukrainian gain, restored operational freedom for drone operators in the sector, degraded Russian air defense coverage, and the intelligence value of observing how Russian commanders respond when a key surveillance asset disappears. Each of those gains has operational and intelligence value that compounds over time. Ukraine listens for Russia's radars. Ukraine finds them. Ukraine destroys them. And the airspace above eastern Ukraine, sector by sector, becomes a space where Ukrainian drones operate with increasing freedom as Russia's ability to see them and engage them is progressively reduced. The front holds beneath skies that Ukraine is reclaiming one destroyed radar at a time.